Hello everyone. In this session, I'd like to explain the evolution of stars. First topic is the stellar evolutions. Second topic is the characterizations of the T-low planes. Third topic is the evolutionary path. Fourth topic is the evolution of a star. Final topic is the late evolutionary stages. First topic is the stellar evolutions. Time scale of stellar evolutions is determined by the rate of consumption of the nuclear fuel. The rate of the nuclear burning increases with an increase in the temperatures. So if you consider the stellar structures, temperature decreases from the center outward. So if you draw the temperature as a vertical lines, and the horizontal line is a distance from the center of the stars, temperature is decreasing. And then we know the rate of the nuclear burning is increasing in the temperatures. So nuclear burning is happening at the central regions of our stars. So evolution of our stars can be understood by considering the change at the centers. So central region, temperature and density increasing. So if you follow the change of the temperature and density at the centers, we could understand the evolution of stars. The next topic is the characterizations of the T-low planes. The T-low plane is divided into zones determined by different equation of state and different nuclear processes. So I show the equation of state can be expressed with the ideal gas or degeneracy pressures or relativistic degeneracy pressure or radiation pressures. I introduced these four pressures. Then we could divide the T-low planes into the zones. So first one is a boundary between the degenerate and the relativistic degenerate gas. So equation of state for the degeneracy pressures is expressed as P sub E dig. And the relativistic degeneracy pressure is expressed as P sub E R dig. To find out the boundary between these two degeneracy pressures, use the equation for the P sub E degeneracy equal P sub E relativistic degeneracy pressures. So from these equations, you can express the densities. Rho is expressed 5 m sub E c over 2h cube times pi over 3 m sub h mu sub E. So you can express the densities. So density becomes a constant value, is independent of the temperatures. So if the density is expressed, unit of the density is a gram per cubic centimeters. Log density is a 6.58. So if the density is larger than these values, we should use a relativistic degeneracy pressures instead of the degeneracy. If the density is lower than these critical values, we should use a degeneracy pressures. Okay, by comparing the two pressures, we could find the boundaries. Also, we could find the boundary between the ideal gas and the degenerate gas. So ideal gas equation is expressed this one, and the degeneracy pressures here. And by comparing these two, so P equal degeneracy pressures. So from this, you can find the density. Becomes a 20 m sub E over h squares and 3 over 2 pi over 3 mu sub E 5 over 2 mu 3 over 2 m sub h k Boltzmann constant 3 over 2 t 3 over 2. So if you take a log, this becomes a straight lines. So log rho equals some constant value plus 3 over 2 log t. So this becomes straight line, the slope becomes a 3 over 2. So again, if you use a unit of rho is a gram per cubic centimeters. Unit of the t is a Kelvin. So we could express the straight lines in the plane of the log rho log t's. And also could find the boundary between the ideal gas and the relativistic degenerate gas. So we compare these two equations. So P equal P relativistic degenerate. So from this equation you can find the rho is 8 over hc cube pi over 3 mu sub e to the fourth of mu cube m sub h k cube t cube. So if you take a log in the both sides, some constant value plus 3 log t. So then slope becomes a 3. Then you can draw the lines on the log rho log t planes. This is the boundary between the relativistic degeneracy and the ideal gas. And finally, boundary between the ideal gas and the radiation dominated gas. So ideal gas pressures and the radiation pressure are compared. So in this case, to express the radiation pressure is dominant, you could consider the radiation pressure is 10 times larger than the ideal gas pressures. We could use this equation. Then, so P rad equals 10 times P. From this equation, density is expressed A mu m sub h over 30 k t cube. So take a log in the both sides. Log rho, some constant value, times 3 log t. So in this case, the slope becomes 3. Also, we could draw the straight lines with a slope of 3 in this case. Then, by combining all the information, you could divide the log rho log t plane into the 4 zones. So in these high densities, low temperatures, relativistic degeneracy pressure becomes dominant. And then in this region, degeneracy pressures. In the middle part, ideal gas determine the pressures. And then at the really high temperatures, radiation becomes dominant. Radiation determine the pressures in the stars. Okay. Then zone of the nuclear burning. High sensitivity of nuclear reaction rate to the temperatures. So if you increase the temperatures, nuclear reaction rate is suddenly increasing. So very narrow threshold you can find. So when the Q is a nuclear reaction rate, is a function of the density and temperatures is expressed. So this nuclear reaction rate is larger than some critical value of the Q sub means. So we could say the nuclear burning starting. So this Q is a Q sub 0, rho m, T to the n is larger than Q sub mean. So this means rho to the m is larger than T to the minus n, Q sub mean over Q sub 0. So take a log in the both sides. So this log rho is larger than minus n over m log t plus 1 over m log q sub mean over q sub 0. Okay, so we discovered this equation. So if you draw the nuclear burning, it's expressed with the straight lines. And if you substitute the pp chains, m equal 1, n equal 4. So this also steep lines because the slope becomes a minus 4. This is very steep slope. But in the case of the CNO cycle, m equal 1, n equal 16, much steeper slopes you could find. Then we'd like to draw the nuclear burning on the log low, log t planes. So PP chain is here, and the CNO cycle has a really steep slope. And triple alpha reactions, and the carbon burning, the oxygen burning, and the silicon burning happening at the high temperatures. So temperature is increasing, then heavy nuclei are burning in the stars. And finally, ion photo disintegrations. Well, I have explained condition for dynamical instabilities. Gamma is adiabatic component. So relativistic degenerate zones and radiation pressure dominated zone is the gamma is exactly the 4/3. So they cannot satisfy the stability conditions. So these zones are dynamically unstable. And also in the degenerate gas, as I explained, nuclear burning in the degenerate gas is thermally unstable. So we don't expect nuclear burnings in the degenerate gas. Then we sum up all the information into the single T-low planes. So relativistic degenerate gas is unstable. So we make a shaded is an unstable region. This is unstable. And also radiation zone is unstable. This is unstable. Okay, and also nuclear burnings, PP chain and CNO cycle, and helium burning, triple alpha reactions, and carbon burnings, and oxygen burning, and silicon burnings, also shown in these figures, and ion photo disintegrations. This figure is very useful to understand the evolution of stars. Okay, this is the end of this session.